So, good afternoon everyone, and welcome to this final lecture in the series on recurrent neural networks. Specifically in this lecture, we will continue the topic of sequence-to-sequence models with focus on attention models. We've already considered sequence-to-sequence modeling. So here is the problem. You have a sequence x1 through xn which goes into the model. A different sequence y1 through ym comes out, and the number of symbols coming out doesn't have to be the same as the number of symbols going in. For instance, speech recognition. Speech goes in, a word sequence comes out. The number of vectors that goes in can be orders of magnitude more in number than the number of words that come out. Or alternately, instead of having words come out, you can output character sequences. In machine translation, word sequences go in and word sequences come out. In all of these cases, in general, the number of inputs doesn't have to be the same as the number of outputs, and there need not be any synchrony between the input and the output. So we've considered CTC models so far. In the CTC models, we assumed there was an order synchrony between the input and the output. Something like speech recognition. Speech went in, a sequence of words came out, and there was a correspondence between the order in which the input went in and the order in which things came out. So the I comes first here. The first portion of this recording would correspond to I, and so on. In machine translation, you have a different situation. Something like I ate an apple goes in, ich habe einen Apfel gegessen comes out. So here, the notion of synchrony is lost. I is the first word here, the corresponding word here is ich, but ate actually translates to a combination of two words, habe and gegessen, which are not only not necessarily in the second position, they're not even contiguous. One word gets split across two positions, so there is no synchrony. We've dealt with the order synchronous problem earlier using CTC models. Here the input and output sequences happen in the same order, although they may be time asynchronous. For example, speech recognition. The input speech corresponds to an output phoneme sequence. Today, we are looking at the second problem, which is problems like machine translation, where the synchrony is lost, as we saw in this example just now. Now, before I continue, we will quickly recap a problem that we've already seen because it's related to the models that we will be considering. And that is the problem of predicting text. Here was the simple problem. You're given a series of symbols, which could be characters or words, W1 through Wn, and the problem was to predict the next symbol, which could be the next character or the next word. So the problem there was to learn a model that can take in a sequence of words and learn to predict the next word, or more generally take in a sequence of symbols, W0 through Wk, and learn to predict what Wk plus 1 was. So you'd have a situation like this. At the word level, the model must be able to see 7 years and learn to predict that the next word is a go, or ABRAHAMLINCOL, and learn to predict that the next character is N. Now, in all of these cases, you have a very simple problem of predicting the next character or the next symbol. And the model that we considered had a structure such as this one. Since the inputs are now symbols, we actually represented them as one-hot vectors, which could optionally be projected down to some low-dimensional representation. What the output of the network was at each time was not a unique character or a unique symbol. It was a probability distribution over all the symbols in its vocabulary. So at each time, each y was actually a probability distribution over all the symbols in the vocabulary given all the inputs until that time. And we could now define a divergence when you were trying to learn this network between the desired output and the output of the network. The output of the network now again is a sequence of probability distributions. The desired output at any time is the next word. So for instance, when the input is just W0, the desired output is the next word, which is W1. When the input is W0, W1, the desired output is the next word, W2, and so on. So you could now compute a divergence between the sequence of words that you're trying to predict and the outputs of the network. And as we've seen from the math in prior classes, if you define this divergence as the sum of the cross entropies between the output of the network at each time and the one-hot representations of the words at each time, then the divergence itself simply becomes the negative of the sum of the log of the probabilities assigned to each word at each time. Now, once such a model is trained, you can use it to generate text. Typically in these models, the hidden layers over here would be represented as one or more layers of LSTM units, LSTM cells. These are trained using back propagation, using lots of training text. And now, when you want to generate new text, and this is the key piece because this is what we're going to keep invoking through this lecture, here's what we would do. You would provide it with some initial sequence of words, and given some initial sequence of words, this is the entire computation performed. It's going to keep recurrently computing the hidden state value, and say W1 to W1, W2, W3 was the sequence of words given. At time 3, the network would produce a probability distribution over all the words and its vocabulary. And from this probability distribution, we would draw the next word, W4. And now, having drawn this W4 from this probability distribution, we could now input that as the next word in the sequence to the network. And the network would now compute a probability distribution over the words that it is predicting at time 5. And from that, you can draw the next word, and so on, and continue till you actually output a symbol that indicates that the sequence of words has terminated. In all of these problems, we have this special end of sequence symbol, EOS, which is a special symbol included in the vocabulary, which indicates the termination of a sequence, and always occurs at the final position of sequences. So this is the synthesis problem. Keep that in mind. We're going to use it. So returning to our problem, here is the problem. You want to input a sequence of words like I ate an apple, and you want to output its translation, which is Ich habe einen Apfel gegessen, if you're translating English to German. So you have one sequence x1 through xn going in, and a different sequence y1 through ym coming out, where there is no strict notion of order synchrony between the two, and even the number of symbols in the two can be different. That problem can be modeled by this version of the neural network. We've seen this before. So you have a sequence of inputs going in, and once the entire sequence of inputs has gone in, the hidden state essentially stores or summarizes all the information about the sequence of inputs. And based on those, now it can go ahead and produce the sequence of words or the sequence of outputs that is best suited to the given sequence of inputs. So this is the delayed sequence to sequence model. So there are two steps to it. First, you'd process the input, which is a sequence of incoming words, which might be the words in English in our case, and generate this value, which is a hidden representation for the entire sequence of words. And subsequently, so here's how you do this. This is the little pseudocode. You'd go through time, and at each time, you compute a hidden value, which is a function of the current input and the hidden value of the previous time. And once you've done the whole thing, once you've run through the entire input, the final value that you compute, this hidden value, is what you will use to generate the output. This hidden value is now going to be used in this portion of the network, which will generate the output. Now, so here's how it would be if you were to write it in pseudocode. The first pass would compute the hidden representation after having consumed the entire input. And subsequently, you have a standard recurrent model which just considers the hidden value at the previous time and uses that to generate a probability distribution from which you can draw the next word. Now this is not exactly how we do it, because there's a problem over here, in that the word I generate at time t does not get input right back into this recurrence step, as you can see from the pseudocode and from the figure. So it means, for instance, that if I generated the word an at the current time, the fact that I generated the word an at the current time has no influence on the hidden state at the next time. So at the next time I could just go ahead and generate the word horse. And we know that an is not followed by words that do not begin with a vowel. So it can break all of these dependencies if I don't actually consider the word that was output. So here again, if you have already generated it was a versus it was an, the probability that the next word is dark remains the same regardless of whether you generated a or an as the last word. And this is because the output at time t does not influence the output at time t plus 1. And so we're going to modify our network just a little bit. And the way we will do it, instead of having this structure, which would be this figure here without this yellow box, which is to say that the input is consumed, a hidden value is produced, that hidden value is then input is used by the second portion of the network to produce a sequence of outputs. We're going to change it to say that the output produced at any time is fed back into the network when the network is in the output producing stage. So the entire computation goes as follows. The input sequence feeds into a recurrent structure, and the input sequence now must be terminated by an explicit end of sequence symbol to indicate that the input is completed. And now the hidden state at the hidden activation when this end of symbol sequence has been observed stores all the information about this entire input sequence, the entire sentence. Subsequently, the second recurrent neural network will use this hidden value and use this as an initial state to produce a sequence of outputs. The output at each time becomes the input at the next time, so the output production continues till an end of sequence symbol is produced. So here's how it would go. Once the input has been consumed, there's a hidden state value. That hidden state value is going to be used by the network to produce the next word, which would be ish in this case. And that is going to be fed back into the second portion of the network, which also takes this hidden state and which computes a new hidden state from which it produces the next output. And that output is going to be fed back in, and this recurrence continues till the output is an end of sequence symbol. So here is the whole structure again. Now in my illustration, I've assumed that there's just one layer of hidden states. In a practical implementation, you can have any number of hidden states. So a real model would be more like this one here. But for all of my illustrations, I'm going to assume that there's just one layer of hidden states. So here again is the pseudocode. Here is the entire process. It's a two-step process. And the first step, you process the entire input recurrently until you get the hidden state at the final time. And then once you've gotten this hidden state at the final time, that is the hidden value that is actually input to the second portion of the network that produces the word sequence. And so this one is now fed back into the second portion of the network as the first hidden state value. And then you have the recurrence, where at each time the recurrence considers the hidden state value at the previous time and the output from the previous time to compute a probability distribution from which the current word is produced. So observe over here that the second portion of the network is basically using the same process that we used to generate word sequences when we were modeling language, which is why we started off by talking about it. Now observe also over here that in the recurrence there's a dependence on the words that were actually generated. So the recurrent output at time t doesn't just depend on the hidden state at time t minus 1. It depends both on the hidden state at time t minus 1 and the actual word drawn as the output at time t-1. That's going back into the network. So this figure here with the boxes represents the entire process. But now, if you consider how the computation is done, you can actually decompose the computation into two components. The first component is the component that processes the input and produces this hidden state value. The second component consumes this hidden state value and goes through a second recurrence and it produces the output. So there are in fact now two separate recurrent networks. The first recurrent network consumes the input and produces a hidden value. We will call this first recurrent network over here the encoder. It learns to encode the input into this value. The second recurrent network takes this encoded hidden value from this red box and uses it to produce the output. So this we will call the decoder. Now, let's look at this in a little more detailed way. First, I've just shown symbols going in. In reality, the symbols are sort of going to go in as one-hot vectors. And the one-hot vectors will typically be projected down to a lower dimensional continuous valued vector through some projection. And this projection matrix would be different for the input sequence and for the output sequence, because the input and output sequences can be from completely different languages with different vocabularies. The projection matrices are going to be different. But what the network actually produces is this. At the first time, it's going to produce a probability distribution over all the words in the output vocabulary. So for instance, if you're translating English to German, it's going to produce a probability distribution over all German words. From this probability distribution, when you output an actual word at the first time instant, you will actually be drawing a word from this probability distribution. And so it is this drawn word that is going to be fed back into the network at the next time. And at the next time, this drawn word is going to be used along with the current hidden state recurrently. And at the next time, the network will produce a probability distribution over words again. And the second word is going to be drawn from this probability distribution. And this process continues until you eventually draw an end of sequence symbol from the probability distribution. Now, clearly, it's apparent that there's a certain degree of randomness if you're just thinking about it in terms of drawing, in that if you don't draw the end of sequence symbol for a very long time, the output sequence can be arbitrarily long. Now, so in terms of computation, what exactly is happening? At each time, the network produces a probability distribution over words, but the probability distribution that it's producing is the probability of the word of the fourth word given the entire input and the first three words. So everything over here that's going into the network is what the output probability distribution is being conditioned on, and the vocabulary is the random variable over which the probability distribution is actually being computed. And it is that probability distribution that you're actually going to be drawing words from. So here is the pseudocode for it. Here is the portion which actually encodes the input. And then you have the standard recurrence, except at each time, the recurrent network actually produces a probability distribution, and the output is drawn from this probability distribution. What exactly is this magic drawing operation? Now, to understand that, let's first consider what is the objective of the whole process. When I give you a sentence in English and I ask back for a sentence in German, I'm really asking for the most likely German sequence given this input sequence of English. So the objective of drawing is to produce the most likely output that ends in an end of sequence symbol. So now, if I have a particular sequence of words, the probability of that particular sequence of words is simply the product of the probabilities assigned to it by the network. So for instance, if I want to look at the probability of ich habe einen Apfel gegessen, then it's going to be the probability of ich multiplied by the probability of habe, which is somewhere here, multiplied by the probability of Apfel, multiplied by the probability of gegessen. I guess I seem to have missed a word, but you get the idea. So the probability of any specific word sequence is simply the product of the probabilities assigned to each of the words in the sequence at that position by the network. And our objective is to produce the word sequence for which this probability, this product of probabilities, is largest. Now there's a little issue over here, in that the probability that you compute at any time is going to be dependent on, there's a bug here, I will fix this, these indices, subscripts must be fixed, but the probability that you compute at any time depends on the previous outputs. So if I change the word that I drew at time 1, the probability distribution that I compute out here is going to be different. This complicates the process of computing the most likely sequence of words. Now, of course, there's still a trivial solution to this, which is to say that at each time, I can simply draw the most likely words. So I have that encoded input. I get a probability distribution. I pick the most likely word. I feed that in. I get a second probability distribution. I pick the most likely word again. I can repeat the process. This is greedy. And this greedy answer simply selects the most probable word sequence at each time until the end of sequence symbol becomes the most probable word. So the pseudocode for this over here is simply going to pick the most likely word at each time, the simple argmax operation. But the problem here is that simply picking the most likely symbol at each time doesn't necessarily guarantee that you're going to pick the most likely symbol sequence overall. And why is that? Because the symbol, the word that I pick at any time, changes the probability distribution at the next time. And as we will see in the next slide, this actually affects the entire notion of what is the most likely or most probable output sequence. So consider this example. Let's say at the first time, the word that you chose was he. At the second time, you fed this word he into the network. It computed a probability distribution, and from that you chose the word knows, because knows was the most likely word at the second time. But then if you chose knows over here, he knows, as if with the second word being the nose, which is this organ on your face, that actually is not a very reasonable sequence. So it's very confusing as to what the next word might be, in which case the probability distribution that it computes over the third word is going to be confused, and it's going to be somewhat uniform and low over all possible words. Now, if, on the other hand, the second most likely word was the word knows with the K-N-O-W-S, if you had chosen the second most likely word, so which means that at time t equals 1, you didn't choose the greedy answer, but you chose the second most likely word. But now here, he knows is actually a perfectly reasonable word sequence, and there is a very nice future to it. And so then you could actually compute the probability distribution over all the words of the next time, and you might find that the word something has very high probability when the first two words are he knows, but then this is the knows with a K-N-O-W-S. And so now, over here, if I pick the most likely of these words, the product of the probability of the first three words, in this case, can end up being much lower than the product of the probability of the first three words in this case, even though for the second word, knows was more probable than this guy over here. And that's because by introducing this knows, which is the organ, we made the words at t equals 2 very confusable, and so it assigned low probabilities to all the words, whereas when you chose this word over here, it actually, the output probability distribution was peaky at a specific word, and just picking that word meant that the sequence of 3 words in the second case is more likely than the sequence of 3 words in the first case, even though the second word here was locally less likely, was more likely than the second word here. And now this can actually continue, right? It's impossible to know a priori which of these 2 words I must have chosen. I gave you a very simple example, but the influence of the word that you choose at any time can actually not be seen until several words down the line. So also, something else might happen. The choice of the wrong word early may cumulatively lead to an overall a poorer overall score than if you chose a different word. In our case, for instance, if the first word, let's say in the first word, at the very first time, the example we chose used the word he. But let's just assume that he was the most likely, but the word the was the second most likely. Now, if you chose the word the in the first position instead of the word he, then it becomes perfectly acceptable let me go back. It becomes perfectly acceptable to hypothesize the word knows with a K at this time, because So if you chose the word the at the first instant rather than the word he, then it becomes perfectly acceptable for the second word to be the word knows, which is the organ, because the knows, and then you can have any number of words afterwards which are perfectly plausible. So which means that by choosing the less probable word at the first position, you would have made the confusion at the third position lesser, and as a result ended up with a more likely overall word sequence. The point of all of this is that it's not possible to simply pick the most likely word at each time. That is no guarantee that, and guarantee that you get the most likely word sequence overall. That's just a greedy solution and may in fact be suboptimal. So there's an alternative to this. The alternate option is to simply randomly draw a word at each time according to the output probability distribution. So you have some probability distribution over here, and you pick words from this distribution. You just draw from that distribution to choose a word, and then you feed that into the network at the next time, and then it's going to produce a new distribution, and then you randomly draw from that, and so on. Now, if you just use this random sampling, here's what the pseudocode is going to look like. At each time, it's going to output a probability distribution from which you randomly sample the next word. In fact, it can so happen that when you randomly sample words in this manner, you might actually end up with an overall word sequence that's more likely than if you simply pick the most likely word at each time. Nevertheless, it's still not guaranteed to give you the most likely output sequence. So to guarantee that you get the most likely output sequence, you have to go one step further. At each time, you want to retain all possible choices. So at time t equals 1, you get a probability distribution over words, but then you retain all possible words. And so now this means that this network must be forked, and you must make one copy of the network at the next time for every possible word in the vocabulary. And so if these are all the words in the vocabulary, I, he, we, and the, then at the next time you'd be feeding all 4 of these guys into this hidden state, and you'll be producing the distribution for the next word. So the distribution that you produce for the next word is going to be dependent on the specific word that's being input. And then this process follows. Over here you have an entire distribution over words. Once again, you don't want to pick. So you're going to clone this guy and make many copies of it, and each of those in turn is going to consider as input one of the words in the vocabulary. So you actually end up with a tree of words, word sequences. And if you could actually just keep expanding this tree, then eventually you could, eventually you could pick the most likely word sequence. But there is a problem. You can't just do this simply. For an output vocabulary of size v, after t output steps, we'd have fork dot v raised to t branches. So this thing is going to grow exponentially. Now we've seen this issue before when we were dealing with the CTC, and we know exactly how to deal with it. And the way we will deal with it is to prune. At each time, you would retain only the top k scoring forks. So at the first time instant, you get a probability distribution. You fork this hidden state with one copy for every word. And then you just retain those copies, the top k most likely copies, which is like the equivalent of saying you're just going to retain the copies corresponding to the k most probable words. Then those guys are in turn going to produce the next word, where the next word you'll be forking over the entire vocabulary. And now, at the next time, once again, if I can pick k words over here, I'm going to have k times v words out here, but then I'd prune that down again and retain only k words. The criterion I'm going to use to decide which ones to retain is not going to be the local probability of the word out here, but the probability of the entire word sequence going to the root. So that's because the probability assigned to any word over here is conditioned on the word output from here, which means to say it's conditioned on this input. Because as you know, in this particular recurrent framework, the probability assigned to any word at any output time k is dependent on the entire input and also on the first k minus 1 words in the sequence. So the probability assigned to each word is going to depend on the parent. And so the score that we would use to decide the top k is going to be the product of the probabilities down this entire line. It's based on the product, and then from that product you're going to retain the top k. And in this particular case, at this time, the first term is going to have a probability of 0.1 given all the inputs. These symbols would have the probability of 0.2 given 0.1, which is the first word and all the inputs. And so the product of these two is the probability of 0.1, 0.2 given all the inputs. This is what you would choose, which is to say this product, to decide which the top k guys are. And once those top k guys have been retained, they would be forked out, and you'd retain the top k from those at each time. You're always going to be pruning based on the product of all the probabilities in the path to the root. And continue this until eventually one of the word sequences ends up in an end of symbol sequence, and then you can just output that word sequence. If you want to have more than one output, if you want to have the top n outputs, then you can continue to extend the ones that haven't yet hit the end of sequence symbol and extend them until you get more symbol sequences that actually hit the end of sequence symbol. Now as a result, when you have a top n output, the different paths, unless you have n paths all ending with an end of sequence symbol at the same output time, the different paths, the top n paths might all be different lengths. So here's the pseudocode for it. Observe that although this process, this branching process seems complicated, in reality, when you actually implement it, it's very simple. This is very much like the pseudocode for the CTC decoder. The only extra bit that we do is that now, in addition to the path and the path score, we also retain the hidden state value for the path. So with every path, you have the hidden state value and the path score. You would prune according to the path score and retain just the top key ones from the list. Now, how do you train such a system? We must make the network predict words appropriately. So what this means is that the network must be able to see I ate an apple and produce Ich habe einen Apfel gegessen. So you want to train the network to be able to produce this sequence. Here's how you do it. In the forward pass, you're actually going to input the source sequence, which will produce the hidden state. And then, in the decoder phase of it, you're actually going to give it the true word sequence. So this is just like the word generation that we were doing when we were learning language models. So at the first time, the output probability distribution is just computed using the hidden state. At the next time, the input to the decoder is going to be the actual word ish, which is the actual first word in the output sequence from which this distribution is computed. And then at the next time, you're going to be inputting the actual word harbor, and so on. So you actually input the true output word sequence, and at each time, you expect to be able to produce the true next word, which is to say that you really want the output probability distribution so such that the true next word just stands out and all the other words have very low probability. So the target word sequence is this guy. At t equals 1, it's ish, 2, it's harbor, then einen, Abfallgegessen, and end of sequence symbol. You would minimize the KL divergence between this sequence and this sequence of probability distributions. And that divergence, you can compute the divergence between the true sequence and the sequence of probability distributions output at each time. And that divergence can now be fed back through standard backpropagation to update both the weights in the decoder and all the way backwards to update the weights in the encoder. In practice, we perform stochastic gradient descent, and so instead of computing the gradients from the entire output sequence, it's common practice to randomly sample words from the output and just use those for the backpropagation. So although here, for instance, you're producing an entire sequence of 6 symbols, 5 words in the end of sequence symbol, you might just randomly sample, say, just 1, and just backpropagate just the gradient over here through the entire network to update all of your parameters. You might sample more than 1, but the point is that you're just sampling a small number. So here's the overall training. Given several training instances comprising input sequences and output sequences, desired output sequences. In the forward pass, you compute the output of the network for X and D. So observe that both the input X and the desired target sequence are being used to produce the output in the forward pass. And that is because, as we saw in the previous slide, during training, this is what we did. We gave it the input, and then we also gave it the desired output so that it could predict the next word at each time. And subsequently, during the backward pass, you compute the divergence between the desired target D and the actual sequence or output sequence Y, and you propagate the derivatives of this divergence for updates. There are some standard tricks of the trade for this one. One standard trick is that the input sequence might be fed in reverse order. So you start with the end of sequence symbol and then go down to the first symbol. And that's because you find that the first output word is more related to the first word in the input sequence. And so by doing this in the reverse order, the intuition says that it's able to latch on to the first word in the sequence more accurately. And this can drive the decode of the subsequent words better than if you just present the input in the correct order. The backpropagation just continues exactly as before, with the only difference being that the input is now being presented in the reverse order. This happens during training, but also during inference, you would be presenting the input in reverse order, computing the hidden value, and then that hidden value would be used for decoding. So here's the overall training again. You're given several training instances comprising input sequences and output sequences. During the forward pass, you compute the output of the network with the input in the reverse order at this time. Again, you'll be using both the actual input, reversed, and the target input for the forward pass. And in the backward pass, you'll be computing the divergence between the desired target and the actual output. And then you can propagate the derivatives backwards, derivatives of the divergence backwards for updates. So here are some typical applications. Machine translation. You want something like my name is Tom going in, and you want the output to be Ich heiße Tom or mein Name ist Tom. So you're translating from one word sequence to the other. But then automatic speech recognition. The input would be a speech recording, and the output would be my name is Tom. So even though this is an order synchronous problem, you can still also use this mechanism, which doesn't assume order synchrony, to produce the output. And this is particularly useful if, for instance, when you're producing the output, your intention is to produce the spelling of the words directly. If you just want to output the sequence of characters, now remember that when you're spelling words, there isn't a direct one-to-one correspondence, order correspondence between the sequence of phonemes and the sequence of characters in the spelling in many languages. So this model might actually be more appropriate than the CTC model if the actual intention is to output the spelling. You can also have this for dialogue systems. In goes, I have a problem, and imagine an automated agent. The automated agent could be a model of this kind. The user calls up and types, I have a problem. The agent analyzes it, encodes the input, and produces, how may I help you? Or you can do this for captioning images. The input is a picture, the output is a caption for the picture. Now all of this is predicated on this guy, this encoded representation that the encoder computes from the input being meaningful. Exactly how meaningful is it? It turns out that it actually captures information very nicely. So here, for example, are encoder inputs produced for various sentences. It has been projected down to 2 dimensions for visualization. Here are several sentences. Now observe this. Mary admires John. Mary is in love with John. Mary respects John. You find that all of those sort of cluster together. They occur very close to each other in the space. In the space of values for this representation. So also John admires Mary, John is in love with Mary, John respects Mary. These use the same words as this guy, but in reverse order, and the algorithm actually figures out that there's a distinction between this sequence and this sequence, so these cluster together and those cluster together differently. So also I was given a card by her in the garden. In the garden she gave me a card, she gave me a card in the garden, they all cluster together. She was given a card by me in the garden. In the garden, I gave her a card. I gave her a card in the garden. Again, this is a different meaning, although it's the same word, same set of words. And again, you find that you get this very nice meaning-dependent positioning of these hidden representations, these sentence embeddings. So it seems to capture this information quite nicely. And in the paper where this technique was first proposed, by Sutskever, Vinyals, and Quaclay, they actually have several examples. Here is one that I grabbed from the paper. Now, let me confess something to you. I'm actually just teaching a camera at this point. There is no audience. But had there been an audience where maybe 1 or 2 people actually understood French, and I tried to read these sentences out, and they could figure out for themselves whether their model the proposed model here actually does a good job of translating an English sentence to French or not. But here are various examples that they've put up in the page. I recommend that you actually go and read them to convince yourself that it's actually quite good, assuming you know French. And if you don't, you can use Google Translate against both to maybe guess which one is more meaningful. I don't know. Here's something that we can actually interpret. This is from a dialogue system, also from the same paper. Here are actually a different paper. This is a neural conversational model, Vinyals and Lay. Now here, the machine begins by saying something. The human says, I am seeing an error related to VPN. This is again a sequence-to-sequence model. The machine has seen the sequence of inputs. It's producing a sequence of output words. And the response is, what is the error message that you're getting when connecting to VPN using Network Connect? The human says connection refused or something like that. And the machine says, may I know the version of the Network Connect that you connect? I'm not sure I know that. Is the Network Connect prompting for any user certificate? So as you can see, the responses are very appropriate. It actually seems to be doing a really nice job. And it's kind of almost difficult to believe that these responses are by an automated system. So the sequence-to-sequence model clearly is doing the job right over here. Here's an instance where a different problem, generating image captions. So this is not really a sequence-to-sequence problem. This is more like an image-to-sequence problem. But the only difference here is that instead of producing an encoding from a text sequence, the encoding is now being produced by an image analyzer, a CNN, which is then fed to the decoder, which produces a word sequence. So here you have two components. The first one is the convolutional neural network, which processes the input and produces an embedding. And then you have the decoder, which uses the embedding to produce a word sequence. So here's how the whole thing would operate during inference. You're given an input image, and the CNN processes it to get the output of the classification layer, which is then fed to the language generation module, which produces a sequence of words. Now, again, the objective is to produce the most likely sequence of words. You could use any of the techniques that we saw so far. In practice, the beam search could be expected to give you better results than either random draws or just picking or just the greedy search. So for training, the process is very similar as you have for the sequence-to-sequence model. Remember, this is an image-to-sequence model. You're given several image and caption pairs. You'd have a preliminarily trained image network, which is trained on a large corpus like ImageNet. And then subsequently, the hidden representation produced by this ImageNet is fed to the decoder, which now considers this hidden representation along with the actual target word sequence to always try to produce the next word in the sequence, exactly like the sequence-to-sequence model for text. And subsequently, you can compute a divergence between the outputs and the target output sequence. Again, observe that, keep in mind that although I'm representing this as a sequence of symbols being compared to a sequence of probability distributions, these symbols are being represented as one-hot vectors. And so the actual divergence that you're computing is the divergence between the one-hot vector for the target word and this probability distribution, which simply ends up being the negative of the log of the probability assigned to the target word by the network at that time. So you compute this divergence, and then you can propagate this divergence backward to learn all of the parameters of this network. Typically, the CNN portion of the network is not modified. You keep that fixed. So here are some examples that were taken from the paper that first presented this work. Here's a picture to the left. That's the caption assigned to this picture. Again, the caption was produced by passing the picture through a CNN, using the CNN's hidden representation, final representation, to trigger language generation by the language generator. And the actual word sequence produced was this: man in black shirt is playing a guitar, or construction worker in orange safety vest is working on a road. Two young girls are playing with a Lego toy. Well, it's almost right. It's not clear that this is a young girl, but you get the idea. Boy is doing a backflip on a wakeboard. They're pretty complicated captions, and they're mostly right. It also gets some things wrong. A young boy is holding a baseball bat. That's not a baseball bat. Or a cat is sitting on a couch with a remote control. I guess it got the remote control right, but this isn't a cat. It makes mistakes. This is my favorite. A horse is standing in the middle of a road. I'm not sure there's a horse there, but yeah, it somehow mistook this guy for a horse. The problem in the captions is not the problem from the language generation itself, most likely. The problem is most likely because the image analyzer didn't manage to interpret the image properly. Now, there are variants to this model. In the basic model, what we had was pardon me. So in the basic model, what we had was this hidden representation was fed once to the network, and subsequently the network just computed the entire output recurrently without further reference to the hidden representation. That kind of has this problem that this hidden representation is seen once and could actually be forgotten as the output sequence becomes longer and longer. So a simple extension is to have this hidden representation feed into the network at each time. Particularly, for instance, if you're doing something like image captioning, this could be fed in to every time during the decoding process. And here is an instance where they actually used exactly that idea to generate captions for images. You have an entire video, and every frame in this video is processed by a CNN to get a bunch of output representations. You take the average of these representations, mean pooling, and this mean pooled representation is fed to the decoder, where it's fed to the decoder at each time, exactly as we saw in the previous slide, to produce the output word sequence. This was from this paper by Subhashini Venugopalan et al. Back in 2015. So here's this pseudocode for this. Assuming that the encoded input is available, the output, the recurrent output, not only considers the hidden representation and the word output of the previous time, but also the encoder output, and continues as before. So basically, you're also considering the encoder embedding at every time. Now, there's a problem with this framework. The problem with this framework is that all the information about the input sequence is sort of stuffed into this one vector. It's embedded into a single vector, which is the hidden node layer at the end of the input sequence. This one node is effectively overloaded with information, particularly if the input is very long. And this can be a problem, because in reality, all of these hidden values carry information. And if you're just stuffing it into one, and even as you pass it downstream, first the information can get diluted. But even if it doesn't get diluted, in the process of getting pushed into one vector, you might actually lose information. You're asking for the network to do a lot of work when it tries to store so much information into just one vector. Also, if you actually consider this guy is a fixed vector which triggers all of the entire output. Whereas if you look at the output words, each of the output words is dependent primarily on a small portion of the input. For instance, ish relates to I. It doesn't really relate to these words. 8 relates to these two words, habe, gegessen. So, but it doesn't, habe and gegessen don't really need to consider anything else. Einen relates to an, Apfel relates to apple. So, the focus of each of the output words over here is on a small subset of the words in the input. Whereas in this basic framework, you're stuffing all of this information into one vector and trying to pass this combined information to the entire output without actually considering what the focus of the word at any time, output word at any time is. Now, if you want to explicitly allow the output, the decoder network, to choose what it must focus on from the input, then the brain-dead solution might be to say that I'm going to pass this hidden representation to every output directly. But clearly that's not going to work, because the output is variable length, so the number of outgoing edges is unknown, and so you cannot have a fixed weights matrix which connects any of these hidden representations to every word in the output. But there's something here, and that we will see in a second. The first step, of course, is that we're going to separate the encoder and decoder, like so. This is just for illustration, but it actually helps us visualize what's happening. Now, the decoder always begins by considering a start of sequence symbol. The SOS symbol represents that this is the beginning of a sentence. And now, instead of just considering a single combined hidden representation from the input. At each time, the decoder is going to consider a weighted combination of all of the hidden outputs, which is going to combine into a single vector. Now, if the weights were fixed, then again, you're back to the original problem, that this weighted combination is one fixed vector that keeps being fed to the decoder at each time. To bypass that, the situation is we're going to do something slightly different. We're going to make these weights with which these hidden values are combined different from time instant to time instant. So at time 0, in order to produce the word 1, it might actually combine these vectors with wi1. So it's going to be h0 multiplied by wi0 plus h1 multiplied by h1 multiplied by wi1 plus h2 multiplied by wi2 plus h3 multiplied by wi3, and so on. So observe that, wait, that's wrong. So it's going to be h0 multiplied by w01 plus h1 multiplied by w11 plus h2 multiplied by w21, and so on. This term within the parenthesis stays constant. So as we've explained over here, as this figure explains, the set of weights used to combine these hidden values at each time is different from output instant to output instant. So note again that the weights vary with output time. The input to the hidden decoder layer at any time, any output time, is now a weighted combination of all of these hidden representations. These weights are scalars. Basically, you're multiplying each of these guys by a number and then adding the whole lot. It's just that the set of numbers is going to be different for each time. Now, we have a little more that we want. We want the weights to differ by time, but not just in any arbitrary way. The weights that differ must consider the current context, what has been decoded so far, because that's what really affects what is most relevant to producing the next word. So the time varying weights that specify the relationship of the output time to the input time is a function of the current output state. So the weights with which these guys are going to be combined to produce this vector that goes into at this time is going to be dependent on what has happened previously, which is to say the hidden state out here. Or for instance, if you want the weights with which to combine these guys at time t equals 4, to produce the output at time t equals 4, then you're going to be depending on these weights are going to be functions of what we already have, which is the state at this time. So you want a time varying weight that specifies relationship of output time to input time, but the weights are functions of the current output state. So secondly, you don't want the weights, you can't just have an arbitrary set of weights, because if the weights are allowed to be arbitrary, then if the length of the input sequence changes, then the weighted sum of all of these guys would just become longer. As the input sequence got longer and longer, you'd be adding more and more terms, and so the weighted h would just keep getting bigger and bigger. You don't want to do that. So you impose a second constraint. You want all of these weights to sum to 1. The weights basically must end up being a distribution over the input, which automatically highlights which are the most important components for producing any particular output. So to do that, we will actually modify the manner in which the weights are computed into a two-step process. The weights with which you're going to combine these input hidden values at any time are computed. As a first step, we will compute a raw value for these weights, which I'm representing as E, and the raw value is going to be computed using some function G. And then these raw values are going to be put through a softmax to make sure that the final value is actually just a probability distribution. So the first step computes a value at each time, which relates to the importance of this hidden value to the output at that time, but then you convert it by putting this entire collection of raw values through a softmax into a distribution which sums to 1, which will naturally sort of peak at the specific locations which are considered most important for the current output time. Now, what is this function g? We have this different, there have been many proposals for what this function g might be. Some of the simplest ones, if this hidden state and this hidden state have the same dimension, then you could just consider g to be an inner product between the two. If they are different dimensions, you could have a weighted inner product, in which case this wg must be learned. Or you could have something more where you actually have a complicated function where you append as each of these hidden values, compute some sort of a nonlinear function like a tan over them, and then combine those together to get the weights. There are different mechanisms. You can even have an MLP, which takes these two values in jointly to produce the raw weight. But then once the raw weights are produced, they are converted to a distribution through the standard softmax. So all of these red values over here are values to be learned. So when I use this process to actually translate one sequence to the other, here's how it goes. First, I'm going to pass the input through the entire decoder to produce hidden representations at each time. And subsequently, from the final hidden representation, I would compute the initial value of the state of the decoder, the state of the decoder at time -1. And there are several ways of doing it. You could just copy this last value over, or you could think of a weighted combination, some weighted more transformation of this last value, or some combination of these. It's often common to just initialize this s-1 as 0. What is really interesting is what happens subsequently. So this hidden value is used to compute the raw weights at each time for each of these guys. And from these raw weights, you're going to compute a probability distribution over all of these inputs. And using the probability distribution, you would compute a weighted combination of all of these hidden state values. And this weighted combination is going to be fed into the network along with the very first symbol, which is just the start of sequence symbol, and the initial state. And the hidden state over here is going to use the combination of these three to produce a probability distribution at that time. And from that distribution, you draw a word. And then subsequently, using this hidden state, you're going to compute the raw weights for all of these guys using S0. And from the raw weights, you'd put the raw weights through a softmax to compute a distribution over all of the encoder embeddings, all the H's, and output a new weighted combination of all of these H's. And that weighted combination is going to be fed in to the network along with the hidden state of the previous time and the word output of the previous time to produce the output distribution of the next time. And at the next time, and from that, you would draw the next word. And subsequently, you'd follow the same process all over again. You would compute raw weights using this hidden state and all of these H's. So you'd get a raw weight for every time instant from which you could compute a distribution over all inputs. And using that distribution, you'd compute a weighted combination of the hidden values, which is going to be fed into the network to produce the next distribution, and from which the next word is drawn, and so on. You'd continue the process until an end of sequence symbol is produced. So observe that this was very simple, very similar to the encoder-decoder structure that we saw earlier in this lecture, with the one key difference that instead of just using the final representation that has been learned by the encoder, we are now sort of using a representation, we are using a weighted combination of the representations computed at each input time. And this weighted combination differs with output time, and that weighted combination, which we will often call a context, is fed to the decoder along with the last word produced and the current state of the decoder. So, as before, the objective of drawing, again, at each time, an output distribution is produced and you're drawing a word from it, right? So the objective of drawing these words is to produce the most likely output sequence that ends in an end of sequence symbol. So you really want to produce, you want to find the sequence of words such that the probability of the product of the probabilities of the words that you've drawn is maximum. And as before, the word that you've drawn at any time affects the probability distribution that you computed the next time. So if you change that word, the distribution is going to be different. And as a consequence, the probability assigned to the next word will change, and so on. So if you want to actually output the most likely word sequence, you cannot just greedily select the most probable word at each time. You actually want to be doing, which is something very similar to what we did in the first case, which is to retain all choices and fork the network with every possible word as input. And of course, we know that this is going to be expensive. So an engineering solution is to prune these choices as before and just retain the top k and then expand the top k and so on. Again, as before, the probability that you use to decide what the top k choices are is the probability of the total, the product of the probabilities down the entire path to the beginning. So the score assigned to each node over here is going to be the probability of the product of all of these probabilities, and you just choose the top k based on the product score, which you would use to prune the paths, and then you would expand the prune paths and so on, and continue till you produced an end of sequence symbol. And as before, if you want to produce more than one output sequence, then after having produced one end of sequence symbol, you can continue to expand the other paths. And once again, this would mean that if you produce more than one output sequence, the output sequence, the top k output sequences you produce may all have different lengths. Now, there's something very interesting that happens over here. In this process, in order to generate any given word, you're actually looking at a weighted combination of the hidden representations computed over the input. So in order to produce y1, as a first step, a probability distribution was computed over these hidden states, and these weights were used to compute a weighted sum of all of these guys. And clearly, if these weights, if the algorithm is working properly, then in producing the word over here, the network must automatically learn which of these hidden representations to focus on. And that hidden representation, in turn, depends on the word at that time. So it must automatically figure out that, for example, if the word out here is harbor, harbor is most dependent on the word 8. And so when producing the word y1, you would expect the weight to be higher out here and lower in other locations. So let's actually visualize how this works. This is for a machine translation task. This is the input. These are the output words. And this row is a pictorial depiction of the weights assigned to each of the input times when producing this word. So you see that the weight is large for the and low for the rest of them. So the network automatically figured out that the most important input word when producing the first output French word was the word the. So also, after having produced the first word, the weights computed over the input, which are pictorially shown here as a surface map, the weight peaks for the word agreement. So that using that weight, the actual output is the word accord. So you can see that in order to produce any word, it actually sort of automatically figures out which input word to most focus on. Now that's not surprising by itself for these first 4 words. You'd expect that the output would focus, to produce the output for any word, you would expect it to focus on a word at approximately the same position in the input. But then you have these situations, for example, the European Economic Area, and in French is written as Zone Économique Européenne. So the order of the words is different. It actually gets flipped. And you find that the attention model actually learns that in order to produce the 5th French word, it must focus on the 7th English word. But to produce the 6th French word, it must focus on the 6th English word. But to produce the 7th French word, it must focus on the 5th English word. It actually even figures out that for some portions of the output, the attention, the manner in which it must pay attention to the input is not along the forward diagonal, but might have other patterns. So here are a number of different similar examples from the paper that presented this work. And you can see that in every case, how the most important input words for any output gets automatically highlighted. And although the general trend is diagonal, top left to bottom right, you get these localized patterns which capture changes in order. Now, in the English to German translation, if you saw Ich habe einen Apfel gegessen, then habe and gegessen you would find both focus on 8. And so you would actually find these non-diagonal patterns as well. The algorithm actually learns to figure out what is important. And in fact, there's a common test when you're trying to train these models. If the attention map, which is plotted over here, doesn't look reasonable, then your network is probably not learning well. Here are some training translation examples that they had in the paper, Badenau et al. In 2016. And I wish I had any knowledge of French. I can't tell you if this is good or not. But here is the source word, and admitting privilege is the right of a doctor to admit a patient to a hospital, etc., etc. And if you actually look at the reference, which is presumably written down by an expert, le privilège d'admission est le droit d'un médecin. If you look at these translations, you would actually find that their model actually produces very valid translations. Training the network. What we've seen so far is how a trained network can be used to compute outputs, which converts one sequence to the other. But then let's consider training itself. Given a training input, which consists of a source sequence and a pair of a source sequence target sequence pair, in the forward pass, you pass the actual input sequence through the encoder, and then you pass the actual output sequence through the decoder, and at each time you try to predict the next word given the previous subsequence of words. So at each time the output is a probability distribution over words. The actual input is the input sequence of words and the output sequence of words, exactly as we had for the simple encoder-decoder model. And the target at each time is the next word. So at time 3, the next word is going to be einen. The input that I've seen is the set of encoders of encoded representations here, hidden representations here, and the words start of sequence ich habe. It would actually compute a probability distribution over words for the 4th position. The target word is einen, but that's actually going to be represented as a one-hot representation again. So you can actually compute a Kullback-Leibler divergence between the two. And so the divergence at each time is simply, so the total divergence is simply going to be the negative of the log of the probabilities assigned to the target word at each time by the network. This divergence can be propagated back through the network. But when you propagate it back through the network, you should also update the parameters of the attention function g, because that is also being learned. Now, the attention function g may not have parameters to learn if you're just looking at an encoder, looking at an inner product between the decoder state and the encoder state. But if you have some extra parameters, such as if you're looking at a matrix in a product, there are parameters to learn, and those must also be learned. Once you compute those divergences can be propagated backwards through the network, and all parameters of the network, including decoder parameters and encoder parameters, can be learned. There have been various extensions proposed to the model, things like local attention versus global attention. For instance, this paper by Wong et al. In 2015, and other variants. There's no necessity that the input must be processed left to right. Most commonly, the encoder is going to be processing the input both left to right and right to left. So you have bidirectional encoding of the inputs. For instance, this paper, Neural Machine Translation by Jointly Learning to Align and Translate by Badanav et al., they actually use bidirectional encoding of the inputs. And in the homeworks that you will do for speech to text translation, you will find that the most appropriate way of encoding the input is through bidirectional encodings, because because you're computing the attention at each time, there's no dependence on the direction of processing of the input. So you want to do the best possible processing of the input, which is to say considerate information gathered left to right and right to left simultaneously. Another trick that is commonly used is that during the forward pass, instead of simply passing the actual target output as the inputs to the decoder, every now and then you actually pass a word that has been drawn from the output. So ideally, these inputs, if you just thought of it as a complete transducer that takes the input sequence and produces an output sequence, the output would not actually, you would not be using the output at all in the decoding phase. These guys would have actually been the real drawn words. The reason we are sort of forcing these guys to be the actual target words is what we call teacher forcing. We are forcing the teacher, the supervision, to be much more explicit when you're learning the decoder. But that can have the consequence of having the model become way too dependent on having correct inputs when it's decoding. So to reduce that dependency, we also occasionally also pass in the words that have actually been drawn from the output of the network a certain fraction of the time. This is a standard trick that's employed. So that is what we'll call teacher forcing. Teacher forcing is when you actually feed in the true inputs. You're forcing the teacher to provide the entire sequence of inputs that the decoder sees. That would not happen during actual inference. And the relaxation over here is that even during the forward pass, occasionally you actually use the output. The problem here is that the process of drawing a sample from a distribution is not a differentiable process. So there's a trick called the Gumbel noise trick, which makes this drawing differentiable. I recommend that you look this up. But now that actually means that you can have derivatives passed down here and go back up here during the backpropagation process. Now this entire sequence-to-sequence model, as we just saw, has had some very impressive results. Attention-based models are currently responsible for the state-of-the-art in pretty much any sequence conversion system, like machine translation, speech recognition, dialogue systems, you name it. It turns out that or natural language processing. It turns out that these models are highly effective, and regardless of which task you look at, the odds are that you're going to look at some variant of this in the model. In fact, it turns out that you can extend the whole approach one step further and get rid of recurrence altogether and make your entire processing attention-based. This is the model that's called the transformer. That will be covered during a recitation. I won't be covering it in class, but I recommend that you look it up. So here are some very nice examples of attention-based processing. This was for image captioning. Now, in the example that we saw, the attention was being paid to input text to produce output text. But the same concept can be used to pay attention to different portions of an input image to decide how best to represent the image to produce the next word in a sequence. And so here, for example, this image, the caption produced for this image is a woman throwing a frisbee in a park. And if you look at the attention map that was used when it produced the word frisbee, it actually focuses on the frisbee. Or a group of people sitting on a boat in the water. The sequence, the attention-based model was used to generate a caption for this image. And if you look at the attention map that was used when producing the word people, it actually focuses on people, and so on. You get these very nice, the attention mechanism is actually able to pick up the appropriate portions of the input to highlight to produce the next word. So in closing, so far we've looked at various forms of sequence-to-sequence models, which are generalizations of recurrent neural network formalisms. For more details, please refer to papers on the topic and post on Piazza if you have questions. This is going to appear in homework 4, so we have a couple of recitations devoted to it. The homework 4 is going to be speech recognition with attention models. Let's stop right here. Thank you.